So hi everyone. So yeah, I've been taking like a long break from streaming, but I can sort of at this point I think pretty confidently say that the regular schedule is gonna come back. So I should be back doing like streams like once a week, and writing like a lot more frequently. So yeah, I mean it feels like super good to be back. So I figured for this one, this has been a topic I'd been thinking about for a couple of months now, and it's basically like design patterns. So what are design patterns? Design patterns are basically ways of structuring your code to do things that are like commonly useful, right? So basically, and instead of sort of talking about this like thing in a sort of an abstract way, I want to go over some patterns that show up a lot in machine learning code and show you how they work. And a lot of them seem more complicated than they actually are. Like a lot of them have fairly short implementations, but you'll understand a lot. You'll understand about like how to implement things like callbacks, how to implement like decorators, like iterators, how to implement like job queues, like workflow schedulers, like Airflow, like batch inferencing, batch processing. So there's like it's gonna be very broad. Saika-san, thank you so much. Hi. So there's gonna be a lot of stuff that we're gonna be going over. So yeah, I mean, like let's do it. Like without further ado, like let's just get started. Uh, no, so this is not a speed run, although that it is seeming like a lot of people want me to be giving speed runs. So it seems like it's been like a popular thing, and maybe I'll do a lot more of it. So the speed run is gonna happen on the 19th of this month. I'm actually gonna have Sebastian Ratzka also join us, and I'm gonna be going over his 800-page book on scikit-learn and PyTorch in one go. So we're actually not going over the so don't confuse this session with another book called Design Patterns, like an O'Reilly book. I didn't even read that book. Maybe I'll read it at some point, but uh, well, this could be going over like patterns from my head at this point. So before the stream started, I actually went like I wrote down two different patterns that show up a lot. So the first one is called the pipeline pattern. So what the pipeline pattern is basically about like processing data in some sequential way. So for example, oh, thank you for the subscribe. So it's about processing data in some sequential way. So let's say in the case of machine learning inferencing, let's say you have some text, but now you need to turn this into like a tensor so that you can actually, let's say, run PyTorch on it. And then you want to maybe run a post-process function. So turn that tensor back into like another string. So what those functions may look like is like pre-process, inference, post-process, right? And the way you'd actually run them is literally like in the pipeline. Let's say this is just a Python list, and then you would have all the functions that you want to run. And then you would basically step through them one by one and execute that function on your input and keep doing it. So there's sort of two important details here. Like two important details are that the input and output types of functions in a pipeline need to match. So that's the first. So yeah, I'll say an important detail. A function needs to match. Yeah, and yeah. So the reason why types are really important here is because like if you look at this, I straight up gave you oh wow, thank you for the subscribes, folks. I really appreciate it. With Prime too. Fuck. Thank you so much, folks. Really appreciate it. Uh, So the interesting thing about this framework, even like just showing you this sort of covers like a fairly large space of what a pipeline would look like within the context of machine learning. And the reason that's the case is because we're actually using here, maybe I'll show you a bit more. So if you were to say from typing import union, you can actually now set types in Python. So what a union is, it's basically saying the input is either a string, like text, or an image, or a video, or an audio signal, right? So we would basically also have some library from which we get those types, or we would like define them ourselves. Uh, but the point is that like whatever you do here, like once you do this pre-processing, you eventually want to end up with a tensor. So, maybe if you're a careful reader, then you may also think like, well, like, hey, Mark, like, what about batch inferencing, right? Well, The thing is about batch inferencing is it's still just a tensor because you could stack like multiple ones on top of each other. But realistically, what this would mean is that you could say like, well, I have a list of these things, right? And that would be like sort of a more like real world scenario. Uh, how would you make the so let's see, let's leave it as an exercise to the reader. An exercise to the reader is to make the above work with a batch of examples, right? So here's a bit like a slightly more complicated one. So a workflow is sort of a more complicated version of a pipeline. So a pipeline is basically sequential. So it's saying like here pre-process, inference, post-process. Whereas a workflow is really a DAG. So it's sort of saying like, well, input needs function A executed on it, and then the output of A is then piped to B and to functions B and E, and then the output of B is piped to C and D. So hey, Infinity. So today we're covering design patterns in machine learning. So basically typical software design patterns, but with a specific focus around machine learning. So this is what orchestrator. So this is what DAG providers like Airflow, Metaflow, and the ensemble support in like TorchServe do, right? So in this case, like we're actually setting up a DAG as a Python dictionary, right? But if you don't like Python dictionaries, you can also create a DAG using YAML or like let's say Python decorators, and I'll go over how to implement decorators in a second. So basically, instead of like having the structure, you could annotate a function and say something like step 1, step 2, step 3, etc. So once you have this DAG, what a workflow engine would do is it would take this DAG and then it needs to basically figure out like what are all the steps that need to run, right? So basically for key value in DAG.items, you would say step key value, and then you basically start running. So the way a step is, what a step is, a step has some inputs, it has some outputs, it has some dependencies, right? Like you can't run on the inputs unless they're already available. Once those dependencies are met, you start executing a function, the step. And then what the workflow engine needs to do is make sure that the steps are orchestrated among each other. So a real world orchestrator, and maybe like this could easily be just like the whole topic of a 1-hour session. A real world orchestrator would need to take care of dependency management. It would also need to take care of scheduling and resource allocation, right? So basically, a step doesn't just like have a like a step could have like some resources associated with it. So let's say we say self.resources. Like this could be like a dict that essentially also has like, I don't know, CPU 1, for example, GPU 2, something like this, right? So, and then you can imagine like resources could be its own class as well. And you could do something like this. Maybe more realistic. Let's still have something like this. Right. So another design pattern I want to talk about is this idea of function as data. So this comes up a lot for Lisp programmers. So a function as data means, like let's say you have a function, like so this is Lisp, and the way to read this is you say like I want to run the addition function on inputs 1 and 2, right? So this is just Lisp syntax. But if you add the quote here, so if you put this at the very beginning of sorry, I think it's this quote. Sorry, if you put this quote before an expression, it's no longer like you're telling Lisp don't evaluate this, but just treat this as some data, right? So the powerful thing about this is that like, well, let's say now you have this line, this string that says parentheses +1, 2. You could basically now create your own compiler, right? Where you could say something like, well, I'm going to look at this string, and I'm going to realize here that it seems like the inputs never change, and the function plus is a pure function. That means that given the same inputs, it's always going to produce the same outputs. Therefore, I can now replace this plus 1, 2 with 3, and just evaluate that. So I've replaced like a function running by just like a value. So this was a bit long-winded. The reason I'm saying this is because PyTorch actually has a very similar idea. So if you've used PyTorch before, it's going to have something like this. So it'll have something like Python, right? So then you can have like class, and then let's say Python. Wait, why is this not rendering? Sorry, here. Yeah. So let's say we have like model, like my model, and then this is a torch.nn model. And then you have like your init, self, and then in this init, you're gonna have self.linear equals torch.nn.linear, let's say 100, something like this. And then if you also do like, so you're gonna have a forward function, right? And then what this forward function is gonna do is gonna take like some input, and then you want to say output equals self.linear on input. And then return output, right? So this is sort of like a very simple kind of model. But think about this for a second, right? So when we later then say, so let's say, so first here, let's define a very simple toy model, right? So we have this toy model. And the way you would typically now use this model is you're going to say something, run an inference with my model, basically torch.randn, let's say something like this, right? So it's a function, but also if you were to run my model.data, you would get the weights of the model. So it's also data. So a function equals data, right? So, oh, thank you. By being bits, thank you for subscribing. Wow, so many people subscribing today, folks. Like, thank you so much. I'm really grateful. So yeah, so the reason I want to bring up this analogy is because this is also very useful if you're designing like something like an inferencing framework, right? Like, yeah, you are running a function, but also it has the weights. So now if you have the weights, for example, you could change them, and then you've created a new function, right? So this is like a very powerful framework, and at least like for me, it was a bit mind blowing when I started to see this idea of function equals data applied to Python. So these are the ones like I did before the stream, just to sort of give you a color of what we're gonna be discussing. But let's do more, right? Like let's do, for example, like an iterator. So let's do the iterator. So how does the iterator design pattern look like? So basically, you would say something like Python for I and range of 10. Let's say print I, for example, right? But realistically, like often like you're gonna want to do something like but a more useful operation would be something like Python, and then for batch in dataset, and then model batch, right? Something like this, right? So you've probably done something like this like a lot. So how do we design something like this, right? So how do you make something like for and available for your classes? So let's say like we're gonna create like a class called dataset, right? And what this dataset is gonna do, it's gonna have like define init, And then we're going to define another one called iter here. So let's just quickly Google of this to create an iterator. Yeah, so we want to create iter and next, I believe. Okay, iter and next. Self n equals 0. Let me minimize this quickly. Okay. Here, define next. We do this by implementing the iter and next functions. So let's see, how does this work? So init class implement an iterator of powers of 2. So self n equals 0 and then return self. Okay. So if self.n is equal to is less than self.max, return result, else stop iteration. Oh, I see. Okay. So let's say something like this. So let's say the data set, we're going to implement it in a very simple way. Equals data. And we're going to make this just like here, we're going to say this is just like a list of some string, for example. So if it's from typing import list. Right. So now that we basically have a list of strings, what we want this to do is we want our iter now to say self.n equals 0. What's n here? I feel like this is missing something, right? Okay, so I guess like iter seems like it would return the very first one. So then we want to say this is return data 0. All right. And what this guy will do is, let's see. So next will num equals self.num. Okay. Oh, I see. So, oh, like we want to keep track of the n, right? Like which element are we at? So self.n. So let's see, where is it? So self.num equals 1. No, self.iterations, self.elements, let's say, for example. Let's say this is equal to, like now this is equal to 1 because we're returning one element. And the way next would work is we're going to return like another element. So the way this will work is just say something like return, let's say, so we say self.elements equals self.elements plus 1, return data, self elements. So maybe we don't need this then, right? So say something like self elements equals 0. And then we can remove this. And great. So now we've basically created like an iterator. So actually no, this is wrong. So self dot data self dot elements. Yeah. Great. So this is like, for example, how we would create an iterator. And so I had a couple more ideas of stuff we could do. So we talked about models as data. We talked about this. We talked about pre-processing. We talked about pipelining. Oh yeah, let's talk about job queues for a second. Job queues. So the important thing to keep in mind with job queues is like, let's say we're doing something like let's say we have a service that needs to pick one of n PyTorch models to run on some input, right? Um, so the way this would work is, let's say we're gonna have a notion of a job. So Python. So let's say we have a data class. So data class is just like a function without I think it's like from data class import. So data class. Uh, and then in this data class, we're going to have a class called job. And what job is going to have is it's basically going to have like the model. So model, for example, could be like a string to determine like which model this is going to be. It's also going to have like what else could it have? Basically like an input. So this would be like a union of a, remember we did this, like a string of image, audio, video. So far it returns one element of the data set. So Sika-san has a question. Yeah. So far this returns like a single element. And I guess like the question is, how do we make this like a batch, right? And so if you want to make this a batch, so then you would say like batch, and then this is an int, which by default is equals to 0. And then you would say if batch greater than 0, else. So yeah, you tell me. So then it's going to be self.elements equals self.elements plus batch. And then we're going to be returning like a chunk of data, right? So we're going to be returning self.data from n to batch. From n to n plus batch. So this is going to be from self dot self dot elements to self dot elements plus batch. Maybe I'm missing one somewhere. Right, so something like this. So this is basically for, I'm pretty sure there's a typo here somewhere, by the way. Okay, so back to this whole business around jobs, right? So we're gonna have like models or inputs. Like maybe the model is hosted on some endpoint. So maybe like endpoint, right? So an endpoint would be like a tuple of a string. So this is the URL and a port, which is an int. So this is like URL port, right? So let's say, so this is how like a lot of like, let's say if you're, I don't know, designing something like SageMaker or something from scratch, like they'll have like some sort of data structure that looks a bit like this. And so now when you're trying to submit a job, you basically have like basically a class called a job, let's say a job processor, and define init. And then this is gonna have a list of jobs. So self, and then self.job equals, so there'll be like a list of jobs. So let me make this clear. This is why like type Python is so great. So it's gonna have a list of jobs, and then what it's gonna do is basically gonna process them, right? So define process job, and you're basically gonna do jobs.pop, and then you're basically gonna execute job, right? So in the case of like in the case of machine learning inferencing, define execute could be something like job.model, right, on job.input. And that's pretty much it, right? So we, um, yeah. So with only a couple of lines of code, we've designed a multi-model inferencing framework. Right, and this is kind of like what I want to show you, like why I find this sort of content interesting. Like I don't think I've seen too many ML books sort of have this perspective on how to build stuff. But once you start like formulating stuff this way, it sort of makes a lot of open source projects a lot easier to understand. So obviously, like frameworks like SageMaker or TorchServe are far more complicated than something like this. But they work in like much the same way, right? It's just like, and then you can, let's say, so then expose. Let's see, I'm gonna say something like this. So output, and then output basically, and then you would say something like expose output on some endpoint, for example. And then again, you would define expose, all right? And then, so this takes in an output and an endpoint. Execute takes in a job. Um, so the output here, for example, so this is gonna, let's say, return the output. Okay, sorry. So here, job input. Yeah, okay. So something like this, and then maybe, I don't know, use last API or something. So the interesting thing about this is, like, let's say you're not using Python to design this job manager. You can also still just spawn a Python process, run the inference, and then write it either to disk or standard out and pick it back up from the other language. So for a lot of frameworks that, let's say, where the backend may be implemented in Python, in Java or C++, like that's exactly what they would do. So it seems kind of ridiculous, right? Like, how do these systems interact? Like, yeah, they just like write files to disk. Okay, so let's see. So multiple input. We talked about like sharing a web service. We talked about iterators. Let's talk about callbacks for a second, right? Like, I think, yeah, so let's talk about callbacks. So many trainer loops will implement callbacks where you can trigger some behavior if some condition is fulfilled. For example, so Python. So it could be something on training ends do something. Or it could be something like on epoch end do something. And do something could be like, like you could basically have something like do something, and this function can do things like store logs, like basically save logs to TensorBoard. It could be something like change learning rate. Well, what else could you do with a callback? So save logs at TensorBoard, like change the learning rate. Yeah, I mean, like I guess those are like sort of the most important one. I recall yield being useful at some point. Yeah. Yeah, let's cover yield in a second. I guess we can do that. Let me just like finish my thoughts here. So the reason I think callbacks are interesting is because they sort of let you like implement like custom behavior without like changing your code too much. A callback is really a particular wait, what? So is a particular case of something called the observer pattern. So let's implement that. This is probably like one of the most complicated patterns here, but let's see on Discord. Where was it? Uh, where was it? Amazing links, yeah. Observer usage in Python. Yeah, let me link. So this is here. Code paraphrased from. Okay. Okay, so we're at the observer pattern. Okay. So check this out. So there's going to be essentially so an observer needs to subscribe to some subject that changes its behavior, right? So to make things a bit more concrete, let's say you have a class. Pseudomates, could you take a look like, well, what are people hoping to do with the Discord command? I don't have much context there. Class like subject, right? So what the subject wants to do is it wants to basically, it either wants to attach people to it, define a detach to it, and then notify. So what does this really mean, right? So the way here, like let's say concrete subject. So let's say that you have like some state. Basically, like let's say this could be the trainer, right? So something like this. So your state is a trainer, and initially this starts off as none. And then you have like basically a list of observers. So observers, which is a list of an observer. And initially this is also equal to none. So this should be my init function, if I believe, yeah. So define and then define init. Right. So what attach is going to do, so basically all of these take in self. So attach takes in self and a new observer, right? So this is going to be a new observer. Detach takes in self and also takes in an observer to remove. And notify doesn't take anything. Oh, Hector, thank you so much for subscribing. Subscribe for 4 months. Like, wow, thank you so much. That really means a lot that you'd listen to me for that long. Thank you. All right. So if we want to basically add a new observer, like, okay, so remember, so this is feeling very abstract, but bear with me for a second. So a subject is something that we're observing, right? So let's say this could be something like a trainer, like basically like a trainer may includes everything about the model, which epoch it's on, loss, model weights, etc. So pretty much like everything you can think of includes model, and then pretty much, yeah, like I said, like everything, like everything possible. And the observers are basically the number of like different classes that can like look at this. So if you want to attach a new observer, well, that's really just like observers dot depend observer observer, and what detaches is its observers dot remove observer. So let's see if anyone can guess what notify is. So notify will basically be for observer and observers. Notify, right? Like trigger, you want to say something like observer dot update, right? State. I don't know why this is in there. So again, like it's kind of crazy to me how simple some of the stuff looks, but like how powerful it actually is. So remember, what did we do? So let's say this, like the subject was like my model, uh, model subject. Let's call it model subject. And let's call this like model observer, I think. Like let's make it a bit more right. So let's say we have like this model observer. Um so now like let's say something happens, right? So the state changed. So pretty much anytime the state changes, and then like we're gonna notify, it. So what does the observer look like? So then you subscribe to some subject. The observer is notified of all state changes of the subject, and then needs to do something when that happens, right? So for example, like let's say you want to create a class, change learning rate observer, right? So this would basically define have init self, pretty much nothing, I guess. I mean, let's say this, like basically it could have like self dot learning rate equals 0.1. What's different between observers? Yeah, so like I'll clarify like a few different examples of observers. I'm going to show you how to do an observer that changes the learning rate, and then another observer that would like add some logs, for example. Um, so the benefit of this approach is that you can extend functionality of a library without changing the core code. You explicitly code the difference exists. Yes, exactly. Like so Roger's correct. Like you actually have to implement whatever that does. So uh, first off, like define update self, and maybe now is a good time to talk about like concrete versus abstract implementations. So at a high level, an observer is an abstract class that implements a function called update. So it's going to say something like Python class observer, and then it has like some init, and then so this implements from ABC. So then from abstract class, I think import ABC. Is that what this was called? Abstract from, oh, it's actually called from ABC. So there's abstract method. Oh, I see. So from ABC, import abstract method, and ABC, which stands for abstract class. So it's gonna basically have some this, and then I guess, oh, it doesn't actually need this. So it just needs an update. Define update self, and then this is an abstract method. Um, so back to the question by Psychosam, and let me know if that's not the right way to say it. So basically, implement your own observer here, and then here pass, because there's no implementation. So then what this happens here is that this is going to inherit from observer. It's going to set the learning rate, and then in its update function, it's basically going to look at the state, right? So basically, let's say it also keeps track of the old state. Let's change the total learning rate. So basically self.state. So this is, like we said, this was a trainer state, for example. And then initially this is equals to none. So what update is going to do is going to say, well, if self.state equals none, pass, else state, so you update the state, and after you update the state, you're basically gonna, so yeah, so let's do this actually. So we're gonna have, how are we gonna do this? I'm gonna call this new state. So then you might want to say if new state dot loss is greater than state dot loss, state dot loss, state dot learning rate equals state dot learning rate times 0.1. Right? So okay, so yeah, so this is how we make things a bit concrete, right? So let's take a look at what happened here. So what the change learning rate observer is doing, and this is a very simple one. You could build very complex ones, and that's how PyTorch Lightning does them, for example, is you basically say, well, I'm going to keep track of two different states. I'm going to just keep track of the loss now and the loss when the state was changed. If the loss now is higher, I'm going to make the learning rate smaller. Like, do not use this in production code. This is education. Right? So yeah, we can then build specific kinds of observers by implementing the update function. And in the example below, we build an observer to adjust the learning rate of a model when the loss increases. Okay, so, but this is a powerful framework, and we can also implement something like logging without changing the library code. And I can't stress how important this is, like, because you can't just you can't change like the core code all the time, right? Like, because then you need to get it merged. You like it needs to pass high quality, etc. So instead you could do something like this. You can build like Python, and then we're going to build like another observer. We're going to basically like log observer, define init self, and then self.state trainer state equals none. And define update will basically take in a new state, and then it'll say like, let's say let's say the new state is a dict. Like actually, so let's say under the hood, it's really like, I mean, we kind of need to implement the trainer state, but you could say something like basically assume new state is a dictionary. So here, actually, you would also have like, let's say some sort of log dir, and then by default, this puts things in logs. Right, and then what you want to say is with what was it? So what was the syntax again? With file as f, and then f dot write. Yeah, so then for key value in new state dot items, f dot write. Yeah, so with open file name, I think it was also right. I think that's right. And then so we're gonna just craft an f string, which is basically gonna be the key value, right? So I implement a logger, right? So, and again, like library without changing the core code, which may require you to get a PR merged in by the core team, that may make the core code unmaintainable by adding all sorts of use cases that people care about. So the observer pattern is primarily a way to extend code, which is why it's very popular in training frameworks like a Fast AI or PyTorch Lightning. Oh, sorry. Oh, yeah, I should do that. My bad, yeah. Why won't this work? Oh, did I have it locked? Okay, wait. To display capture, lock. Oh, sorry about that, yeah. Okay. So this was this was the longest section, I think, actually, by far. Okay. So let's see what else is left. So we did callbacks, we did pipelining, um, multiple dispatch, the tensor pattern, learner pattern, metric pattern. I think this we don't need. We did this data frames. Maybe I'll do some other time. But if you're curious here about optimizers again, like I showed you this as a callback already. We talked about this. We talked about this. Um, okay, maybe okay. So there's still the parallelism stuff left. Matrix multiplication autograd. Maybe I'll do some other time. So this we did. This we did. Okay. Okay, I'm kind of surprised. Yeah, so for autograd, let me do this. Like so autograd. Let me just add it to do section. To do autograd. Let's talk about the learner pattern, right? How does that work? So learner pattern was popularized by frameworks like scikit-learn that started an approach to modeling that was as simple as model.fit on data, right? Um, so I guess here, like this is really like there's sort of like no black magic here. It's really primarily just like the way, like it's the idea like you take some inputs, do gradient descent. Uh, but implementing code for this, at least within the context of neural networks, is something you already do if you've used vanilla PyTorch without a training framework. All right. So by without a training framework, I mean, so let's say we basically like let's write up the class, right? So we're gonna have a class called model, right? Model is going to have what, right? So then it's gonna have some function called fit, right? Let's think about what that is exactly. So fit, we know, takes in some data, and then it returns um, an output, right? So it returns weights. I mean, yes, it's going to return a torch.nnn.model, right? Something like this. Or no, would it returns none actually, because it's just going to update the weights. Yeah. So it returns none. Never mind. So let's say we have here like self.model equals torch.nn.model, something like this. And then the model itself like let's say I'm gonna make this a bit more general. So are any new so AI Infinity is asking any newer, cooler libraries similar to Fast AI and Lightning? They're nice, but I haven't seen much development in the higher highest libs. And they all seem kind of similar. They do seem kind of similar, right? I think all of them like borrow heavily ideas from each other. Um, like fundamentally, like they're all really like no one's really innovated UI wise outside of basically scikit-learn. Oh, by the way, like the reason I want to show you this pipeline pattern here, it's much longer than I expected actually. Um, this pattern isn't only limited to an inferencing framework, but a framework like Keras explicitly has a concept of a layer. So you can do something like so Python. Ignite was developed by Fair. Why doesn't it have more love? I'm not sure. Like, if you have like any specific like feedback to the team on what they could do better, please let me know. But I do think it's a free market. It seems like. I mean, I think a lot of these teams are smart people, and people just pick whatever they prefer, right? But again, if you have any specific feedback, let me know. Um, so let's say you have something like a Keras model, right? So what this will look like is you basically have layers. So let's say layers is a list, and define a forward would basically be on input. So yeah, I'm showing you how to hack Keras if you want to implement Keras from scratch, right? So you would basically say for layer in a self dot layers input equals layer input return input. Yeah, I mean, I've heard all sorts of opinions on Lightning. At least, like, my take on it is that I generally feel like I'm writing more code instead of less when I'm using it, and I get that it's more production stuff. But well, at least with Keras, like, it felt like the reason I picked it up in the first place is because writing TensorFlow 1.0 was miserable. Oh yeah, and then if you want to say something like define add layer, you would just say self.layers.append layer. So you implement Keras, right? You know, please don't tell Francois Cholet that's what I said. Okay, he'll come for me. But at a high level, I think the important lesson here is that even like small code changes, as long as they sort of create like an experience that people sort of like and like enjoy, you can build a whole library and an ecosystem around it. Because before Keras, that's not how machine learning frameworks looked like. The training procedure. Oh, like you mean like the like just like for the training loop? All right. So I think maybe there's sort of also the distributed patterns. Okay, Saikisam is asking, like, how do you guys learn PyTorch? I'm new to PyTorch and using it for class, and it's a bit hard to go from concept to implementation. You can answer this when you're done. Um, I think I may just let me just do uh, the learner pattern, and I think the other ones um, yeah, like let me like just remind me when I'm done with the learner pattern, and I will answer you because I think the other ones we'll do later. Um, So this is made clear if you've ever pickled a model, which is essentially a method to serialize some Python objects as strings on disk. So again, function equal data. I think it's pickle.dumps, right? Yeah, that's it. Pickle.dumps. Let's say you want to say something like Python my model. So model equals my model, and then model, and then log location. Right? So that's great. So let's just do the learner pattern, I think. And then, yeah. So you're going to have like this fit function. And what fit is also going to do is it's going to say, let's do it step by step, right? So basically, one, compute forward function. So you're going to basically say, basically output equals self.model on data. And so we need to add a bit more constraints around data. So data is a tuple. So let's say, so it's something like this. So data equals a tuple. Actually, maybe let's make it even simpler. So it's a list of inputs and labels, something like this. Right, so the way to read this, so basically, so data 0, 0 means the first, means the first input example, and data, let's say 1, 5 means the label for the fifth input example, right? So those names, yeah. So let's see here. So first you compute the forward function to get loss. So basically loss equals, yeah, so this is going to be loss function. And then like, let's say initially this is just subtract. But, or like basically this would be either a subtract or a square loss, L1, etc. So you get the loss function from basically the data. So but loss function here, we'll look at both. Once you get the loss, like 3 update model, by using the value of the loss, right? So this will give, so what update will look like. So define update self gradients. Loss, so this will 1, compute gradients with autograd, and then self.model dot weights is equal to basically updated weights. So this is like at a high level this is why I think the learner pattern is really powerful. And as you can see, like I mean, like you've like it seems like a lot of you have used the training framework specifically to avoid having to write this from scratch. So it makes tons of sense, right? So I think maybe I may call it now because these are a lot of patterns. Um, Again, I think the most interesting ones are the pipeline. I mean, they're all kind of interesting, actually. I don't know. I don't think one is more interesting than the other. Certainly, I do think at least the observer pattern should maybe a bit like expand your brain a bit and how you think about code. Like instead of writing code to a library, think about creating observers to that library, to some objects in that library as a way of extending it. And I guess like maybe in another stream, like we can do like just like a whole other session on autograd, matrix multiplication, and distributed patterns because I think that's sort of its own thing. Um, all right, maybe should we talk about one more thing? So I give you one more bonus one. Maybe like batch processing. Let's do a bonus one. Uh, are the observers instantiated in the? Yeah, let's do batch processing. Um, yeah. So suppose you'd like to run, like to run model.forward on two different inputs. The naive way of doing this is running model.forward input 1, model.forward input 2. So let me just, yeah, I guess our model, you're right. Python. But this becomes like painfully slow if you start dealing with large number of examples. We're going to do something like for input and inputs, model.forward input. Generally, in numerical code, you should fear for loops like the plague, and as much as possible, try to replace them with batch operations. So instead, rewrite your code as Python, and then we're going to say basically tensor. So how are we going to do this? Like, so it's sort of problematic that we even have this in the first place. Let me think a bit how to show it to you. So let's say you want to do something like this, like basically for input and inputs, model dot forward is called big O of number of inputs. Okay. Whereas if you want to do it in a batch way, you would do for input and input, and then basically let me say tensor. Let's say just torch.tensor. And then you would say tensor.stack input. And then you would then just say once model.forward tensor. Model.forward is called once. Remember, GPUs aren't that great at doing many small operations because there's an overhead to sending data to it. So as much as possible, it's better to batch jobs into large ones to take advantage of speedups. Technically, this is not always true. This can be worked around CUDA graphs, but that's still a relatively new feature. Okay, vectorization, interesting. So for vectorization, it's really that it's again like a hardware thing, like where I don't have like a good necessarily explanation for it, but maybe I'll just like say another thing. Something is another exercise. Vectorization on CPU is also another technique to eliminate for loops by operating over chunks of data concurrently. So for example, some newer Intel CPUs will turn matrices into long vectors and do matrix math on them by using a large instruction with AVX 512. So I think for matrix multiplication, I need to find the good reference. For distributed patterns, I think there was this model parallel hugging face. So this was a good tutorial, I felt. So for autograd, automatic differentiation, step by step. Although, like maybe this, yeah, maybe I need to update this tutorial with some Python code. And matrix multiplication, I need to ask Chris for this. Let me ask him. Where was he? All right, I think, and that's it. So let me get status. And Windows. Okay. All right, great. So I think we're in good shape, folks. Like, thank you so much. Like, I guess like I'm happy to take any questions. So let me see. I think there was a question around. Let's see, where were the questions? Okay, how do I learn PyTorch? Yeah, so I will generally say here like a few things. So one, I think the PyTorch documentation is actually pretty darn good. So I would just like go start there, like go like browse stuff, and see what you'd like to do. The other thing to keep in mind is that it's super easy, I think, in ML to like be stuck in tutorial hell, which is like you're gonna go learn about like the different hundreds of billions difference of architectures that people have. Like you want to try to keep up with all the like latest papers. You want to learn some system stuff. And I just want to say, like, sort of flipping back and forth can be kind of a waste of time. Like, unless you're sort of producing good content around it, I would say that's the one exception. But that's where I think like either having like some projects that you're like interested in, or like just finding a job where like you can align your interests, like basically just get more permission to do ML stuff without having to worry about it. I think that those are probably um the like sort of like the best ways to learn it. Like you like it's hard to just have it be a hobby. Like you need to figure out how to sort of be able to do it for real. I think that's sort of the main one. Otherwise, like I think it's definitely gotten a lot easier. Like the content on ML nowadays is much better. Tutorials are much better. Number of examples is very large. The number of open source libraries is very large. A lot of them have lots of hanging fruit. So there's like no shortage of places for you to go contribute. So yeah, I mean, let's go back. Where is it? Yeah, go for it. But yeah, like I said, thank you so much, everyone. Like I'm super grateful you all spent all the time, and thank you for all the new subscribers. It means a lot. So the tutorial will be like on like what everything I covered will be on GitHub. I think, like I said, the main things I want to add are more tricks around like distributed and autograd and matrix multiplication. So stay tuned for those. Um and then yeah, this was fun. I really appreciate your time, everyone. Thank you, and have a good night.